The chemistry of life. All matter is made up of atoms. Atoms contain protons, which you can see here in red. They have a positive charge. Neutrons, which you can see there in yellow, they have no charge. And electrons, which you can see here, and they have a negative charge. Notice that the protons and the neutrons ball up together in the center of an atom, and that center of the atom is referred to as the nucleus. Electrons orbit around the nucleus. You can see here it's commonly depicted as a series of rings. Each ring represents a different distance from the nucleus and a different amount of energy that each electron will have to do work. Ultimately, the further away it is from the nucleus, the more capability it has to do work. An element is an atom with a characteristic number of protons. So the thing to remember is the number of protons determines which element it is. You can change anything else about the atom. You can change the number of neutrons, you can change the number of electrons, you can just find out it's radioactive, you can whatever. The number of protons is what's going to tell you what element it is. That is the defining characteristic of any given element, an element being a type of an atom. If that atom is neutral, you will find in that atom that it has the same number of protons and electrons. We think of, when we look at the periodic table and we think about these things in theory, we think of the atoms as being neutral. If you are boron, for example, you assume that there are 5 protons. You also assume that there are 5 electrons. You also assume that there are 5 neutrons. If you are to change the number of electrons, let's say we change the number of electrons here in boron to 7, you're going to have an ion. If you change the number of electrons to 3, that's also a type of ion. Having more negatives than there are protons is an anion. If something is more negative because it has more electrons, it's an anion. If it has fewer electrons than there are protons, that is a cation. Okay? You can also change the number of neutrons that an atom has. You keep the number of protons the same, the number of electrons the same. If you change the number of neutrons, you'll change the overall mass of the atom, but you won't necessarily change any of its major characteristics enough to matter. When you start getting really imbalanced, you can start going into radioactivity, but we're not really going to be concerned about that with this class. The number of protons plus neutrons gives you your atomic mass. In other words, for practical purposes, it's weight. You assume that a proton has a weight of 1 and a neutron has a weight of 1. Electrons have mass too, but it's a teeny tiny fraction of the mass of protons and neutrons, so it's practically speaking negligible. So for carbon, for example, it has 6 protons. Its atomic number is 6 to reflect that it has 6 protons. It also has 6 neutrons, so its mass is going to be roughly 12. Its mass is roughly 12. If you look at the periodic table that has the masses on it, it's really going to be like 12 point something, a very, very small additional amount. That takes into account the fact that protons and neutrons don't have a mass of exactly 1. I'm sorry, neutrons don't have a mass of exactly 1, and electrons do have a little bit of mass. But roughly, more or less, you can take the number of protons and neutrons to find out what the mass is. If you have an atom, let's stick with a carbon atom, but you have an isotope where you have more or less neutrons than normal. If you have a carbon isotope, let's say carbon 14, you'll hear about that with like carbon dating stuff. What that means is that carbon's mass, atomic mass, is 14. For it to be carbon, its number of protons has to equal 6. To find out the number of neutrons, you'll simply take the mass minus the number of protons and find out that instead of 6 protons, instead of having 6 neutrons, it has 8 neutrons. Carbon 14, being the one that you carbon date with, it does have extra neutrons, making it slightly radioactive. Radioactive things decay along predictable timelines, and so you can use the amount of decayed carbon 14 that everything that ever lived on the planet had some amount of. It's a naturally occurring isotope that you can help determine how old something is that you find. Atoms are attracted to one another and may bond. The bonding doesn't have to do with protons, and it does not have to do with neutrons. It's determined by the electron count. Electrons orbit protons in the nucleus in energy shells. You call them valence shells properly. Now, just to make this clear, when you look at these diagrams of atoms, you have your nucleus in the middle, and then you have these nice orderly rings that surround the nucleus. This is not the case in real life. In real life, electrons will simply surround the nucleus at varying distances away from the nucleus, and they're swirling constantly in all 360 degrees, all around this sort of sphere. And where the electron is considered to be at any given point in time is a probabilistic thing. It's not even necessarily something we can appreciate always literally. But for modeling purposes, this suffices. You think of this as being in valence shell. Hydrogen has an atomic number of 1, therefore it has 1 proton. If it has 1 proton, we should assume that it has 1 electron. Hydrogen actually doesn't even have a neutron in the first place. Its atomic number is 1 and its mass is 1. Later on in the semester, when we talk about especially things like ions moving or metabolism, we're going to talk about protons moving around. What that really means is a hydrogen without an electron. A hydrogen that has lost its electron is a proton. So this hydrogen has 1 proton, therefore it has 1 electron. Electrons will always settle at the valence shell closest to the nucleus. We call that the lowest valence shell. The lowest valence shell has the least amount of energy. It can hold up to 2 electrons. The second level, as you can see here with oxygen, has more energy and can hold up to 8 more electrons. Oxygen, if you don't know what its atomic number is, you can check it by how it's represented here. You have 1, 2, 3, 4, 5, 6, 7, 8 electrons. Its atomic number then is probably 8. It is 8. So atomic number equals 8. Proton, therefore, means it has 8 protons. Its atomic mass is roughly 16. Because the first shell has the least amount of energy and is closest to the nucleus, electrons will settle there first before it fills up higher energy, more outer valence shells. So you have a nucleus here of oxygen, and you have to give it 8 electrons. You'll fill up the first level first, then you'll go to the second shell. You will put down each, sorry, I shouldn't make those pluses because they're electrons. Here's electron, electron, electron. Distribute them evenly first before you pair them up. So 1, 2, 3, 4, then pair it. 5, 6 in the outer ring, plus 2 in the inner ring makes 8. These inner ring electrons have less potential energy than the outer ring electrons. The inner ring can hold 2 electrons, the outer can hold up to 8. The third level has even more energy and can hold 8 more electrons. Anything larger than that, we're not typically concerned about. This is going outside of the realm of normal A and P type material, so we're only going to really need to concern ourselves with this. The first valence shell can hold up to 2 electrons. The second valence shell can hold up to 8 electrons, so total 10. The third valence shell can hold up to 8 electrons on its own, so a total of 18. Here's a couple more atoms that you'll see commonly represented or commonly found in life: nitrogen and carbon. These are the 4 most common atoms that you'll find in any kind of biological entity. So oxygen, we said, had an atomic number of 8. Nitrogen has 1, 2, 3, 4, 5, 6, 7. An atomic number of 7 electrons. Carbon has 6 protons and 1, 2, 3, 4, 5, 6 electrons. Each shell must be filled before the next shell can be filled. So for hydrogen here, you can't say, well, it already has 1 electron. If it wants to take on a second electron, you can't give it a new valence shell. You have to instead pair it up in the first shell, fill it up, and then if you want to add a third electron somehow, you would then add a new valence shell. When the outermost valence shell is filled, it's the most stable atom. So full outer valence shell equals stable, most stable, but it is not necessarily neutral. An anion could be the most stable form of an atom, or a cation might be the most stable form of an atom. For example, oxygen here can hold up to 8 electrons in its outermost valence shell. It's got a second shell started, so you can fill it with up to 8 electrons. If I added an electron here and an electron here, now the outermost valence shell has 8 electrons. But its atomic number is 8. Its number of electrons is now 10. 2 in the middle, 2 in the inner one, and 8 on the outside. You now have an oxygen with 2 extra electrons. It is an anion. Conversely, if for whatever reason you were to just get rid of this electron, you would end up with a cation of oxygen. Remember, cation is a loss of electrons, which makes it more positive. Adding electrons makes it an anion. It's more negative. So having the outermost valence shell be filled with electrons makes it the most stable, but that does not necessarily mean that it is neutral. Wherever you have an unpaired atom or an unpaired electron in a valence shell and an unfilled valence shell, those atoms are inclined to make bonds. Take a note at carbon with an atomic number of 6, therefore 6 protons, therefore you assume 6 electrons unless otherwise stated. You have 4 lonely electrons sitting out here in its outermost valence shell. Carbon is very, very, very happy to make as many bonds as it can to fill up this valence shell. Bonding always involves the movement or sharing of electrons. So carbon has a lot of spaces to fill in its outermost shell. Therefore, it wants to make lots of bonds. If you have an atom with, let's say, pretend that your atom didn't have that and just had 1 lonely electron, it might be inclined to give that away. so that it has just one valence shell, but it's stable, so it's fine with that. We'll have to take a look at these piece by piece. So as we mentioned, when you move or share electrons, you're going to create bonds between atoms. The most secure type of chemical bond is the covalent bond. In this case, electrons are fully shared between two atoms. When you write out that something has a covalent bond, you'll draw that there's an oxygen with a line between the two oxygens. You may or may not evenly share those electrons. I'll get to that in a minute. But remember, oxygen, so for this example, has a atomic number of 8, therefore 8 protons and 8 electrons. The electron part is what we care about here because we're talking about bonds. We don't care about the nucleus anymore, the protons, the neutrons, just the electrons. So if it had 8 electrons, it had 2 in its first shell, because you got to fill up the first shell first. Then 1, 2, 3, 4, 5, 6 in its outer shell. 2 plus 6 equals 8. Oxygen wants to be stable. It doesn't care as much about whether it's neutral or not. It wants to be stable. So when it is in the environment, if it comes along something that it might be inclined to bind with, something that it can either donate electrons to, take electrons from, or share electrons with, it's going to try to do that. It's going to try to do that automatically. You have one oxygen that wants to make 2 bonds, or share electrons at 2 places, and another oxygen that also wants to make 2 bonds. When 2 oxygens come together, what you'll find is that those 2 atoms that this oxygen wants, it'll start to share from the other one, and it'll also share its 2 electrons with this oxygen that wants 2 electrons. You have a nice, happy sharing situation here. What these electrons do, so take, just to color this electron in, this oxygen is going to share that electron with the first oxygen, with the green oxygen. So this electron, when the purple oxygen was alone, was just going around and around and around and around and around. Now these 2 oxygens have bonded, therefore they're sharing their electrons, they're covalently bonded. So it's going to spend time around both. Okay? The other electrons that the green one donates to the covalent bond is also, spent its whole life around just the green oxygen, but now it's going to go around both. It's going to stay in the second valence shell and everything, but it can spend time in both. If each of these are sharing 2 electrons, this one thinks that it's stable and happy, and this one also thinks that it's stable and happy. This shared happiness creates a very, very stable relationship. Now, sometimes you have this type of bond with 2 atoms, one of which is more electronegative than the other. For practical purposes, for our purposes, we're just going to say that electronegative atoms, highly electronegative atoms, are big-time electron hogs. Okay? They just like to hog their electrons. They're not going to steal anything outright. But when an electron's being shared, it's going to want that electron to spend more time around it than the other atoms. Water is a great example of this. So you have oxygen that binds with 2 hydrogens. Remember, hydrogen has 1 proton, therefore 1 electron. Oxygen wants 2 extra electrons to fill its outermost shell. So it'll bond with 1 hydrogen where it gets an oxygen, or where it gets an electron, and it'll bond with another hydrogen where it gets another electron. Now, the hydrogen is going to share one of oxygen's electrons, same thing over here. So now our hydrogen thinks it has 2 electrons, so it's happy, and oxygen thinks it has 8 electrons, so it's happy. But oxygen is a big-time electron hog. It's electronegative. What you'll do to indicate that is give a little squiggly guy here, a lowercase delta, minus, to show that it's an electron hog. Negative is electron-y, so it holds the electrons. Hydrogens are not. In this relationship, oxygens are going to end up looking partially negatively charged. Hydrogens are going to look like they are partially positively charged. Because oxygen is an electron hog, so hydrogen had its nice happy electron going around. Now it's bonded with the oxygen. So it's going to share, right? Just like we showed with two oxygens. But since oxygen is an electron hog, it's going to spend more time here, and then, oh, I guess I'll go over there. And then more time over here, and then, oh, I guess I'll go back to the hydrogen. More time over here, oh, I guess I'll go back to the oxygen, or the hydrogen. Since the electrons spend so much more time over here, this end of the molecule will look more negative. It'll behave more negatively. Since the electrons in this whole molecule spend less time over here, it will behave more positively. Because you have a slightly negative and a slightly positive end to this molecule, we refer to this as a polar molecule. It has polarity. There is a negative end and a positive end. Now, the partialness of this is important. When you have a polar covalent bond, which refers down here, so an uneven sharing. When you have a polar covalent bond, you have a partially positive end and a partially negative end. Electrons are being shared, just not super evenly. But nobody's stolen electrons outright. Only when you have atoms come together and one atom steals an electron outright from another atom do you have a full positive charge. This is a really important concept for you to remember when you think about dissolving things, when you think about properties of water, and I do tend to ask quite a bit about it on most tests. So here's just another visualization of the same thing I just talked about. So you have some polar covalent bonds where your electrons are shared but spend more time around one atom than another. Go over here, around here. Spends more time over here, so this is partially negative and this is partially positive. If they're evenly shared, that's a non-polar covalent bond. So the electrons here, oxygen and oxygen, they're equally electron hoggy. So they're going to spend the same amount of time around each atom in the molecule. In a non-polar bond, there's an even sharing. Therefore, there's no distinct charges anywhere on the molecule. This one, H2O, has a partially positive and partially negative end. There's no such thing here. The most electronegative atoms that we need to be concerned about are nitrogen, oxygen, and chlorine. These atoms tend to hog electrons very, very strongly. So when you see bonds that involve nitrogens, oxygens, and chlorines, you should think in the back of your head, there might be polarity going on here. And think about how it operates within the context of the cell accordingly. The next type of chemical bond we need to think about is the ionic bond. These are very secure on dry land. When you think about chemistry like in a textbook or in a chemistry class, you oftentimes think by default of these molecules in a dry space, like a clump of salt or a clump of sugar or a clump of whatever sitting out on your desk. In biology and anything having to do with life, you think about things in an aqueous environment. All life has water. There's water inside your cells, there's water around your cells, there's water in your bloodstream. All of the chemical reactions and chemical properties we need to be concerned about are how they behave in an aqueous environment. So it is very, very, very secure on dry land. It can also be very secure in an aqueous environment, but it's not as secure as covalent bonds. What's going to happen is you have two atoms next to each other. One is a big time electron hog. It's very electronegative. And another, which is not very or not at all electronegative. You need a pretty steep gradient here for this to happen. Sodium here, Na, you should learn that abbreviation, sodium, has 1 electron in its outermost valence shell. Chlorine is missing 1 electron from its outermost valence shell. In the way that you see both of these atoms represented, they're neutral. They have the same number of protons and electrons in each of the atoms, but their valence shells are not full. Sodium ends up with 1 on its outermost valence shell. Chlorine is lacking 1. Chlorine is very electronegative. So what chlorine is going to do is it's going to straight up steal that electron. Now, sodium doesn't have this valence shell at all because it doesn't have any electrons in it. So where the electrons are is what makes up the valence shell. So now this is its outermost valence shell. And chlorine's outermost valence shell is full. Chlorine is happy. Sodium is happy. They are not neutral, but they are happy. Now, because chlorine stole 1 full electron from sodium, this end of the molecule now has a full negative charge, and you represent it with a minus sign in a circle. Full negative charge. And sodium now has a fully positive end because it flat out lost an electron. When you take a magnet and you attract a positive end, or put a positive end next to a negative end, they attract. They attract quite strongly when you have full charges. This is what keeps sodium and chlorine bonded together in a grain of salt, for example. Now, what's interesting is, we're not talking about grains of salt. That's a dry land kind of thing. We're talking about this stuff in the aqueous environment of the cell. This has positive charge, or sorry, this has a negative charge. This has a positive charge. But you're floating around in a sea of H2O. This is partially positive, partially negative. Partially positive, partially negative. Floating around in a sea of this. I'm going to actually draw this one a little differently just to make this easier. Oxygen, hydrogen, hydrogen, partially positive, partially negative. The fully positive sodium and the partially negative end of the water molecule, the oxygen end, are going to also be attracted. The fully negative chlorine and the partially positive hydrogens in water are going to also be attracted. Now, these two have a pretty strong attraction, but you know what? They are so greatly outnumbered by the water molecules in the solution that the sheer force of these partial charges can split up your sodiums from your calciums. They'll keep rebonding with one another if they get close enough to each other, but as these hydrogen molecules in the water bounce around and come close to the negative side or the positive side or the partially negative side or the partially positive side, it's going to end up forming and releasing these quick little bonds with the sodium and the chlorine. In fact, they're going to keep forming and releasing these small little bonds as it moves around between water molecules. So this hydrogen is going to get attracted to that oxygen. We'll talk about that in a minute. The fact that this positive atom and this negative atom will dissociate in water because of its attractions to the more abundant water molecules is the basis of true dissolving. If you don't break up these molecules, you don't really consider it to be dissolved. Hydrogen bonding is what I had just alluded to in the last slide. You have all these molecules with partial positives and partial negatives on them, partial negative ends and partially positive ends, water molecules being your classic and frankly most abundant example. As these molecules, there's 1, 2, 3 of them, bounce around in the watery solution. Remember, liquids have sort of a medium kind of energy solution, a situation, and so the molecules are moving, just not so much that it turns into gas. The partially negative ends of the molecule, when it gets close to the partially positive ends of the molecule, will form a brief fleeting attraction. You represent that brief fleeting attraction, which are individually quite weak, by a dotted line. Now in this illustration, the dotted lines are like this, but if you were to try to draw that on a test or something, you're not going to be able to tell. It's hard to see. Sometimes it looks like a full straight line, which you use to represent a covalent bond. What you're going to do is instead represent it with these big fat sideways dashes. It's just easier to see on a test, okay? Individually, each one of these brief fleeting attractions are weak, but there's so many of them that collectively the force of those hydrogen bonds become pretty strong. The sum of all these hydrogen bonds between the bouncing around molecules of water is what creates surface tension. You can float on water. You can see a bug like walk on water where it doesn't even break the surface because of all of these fleeting attractions. They become fairly robust. Ionic molecules can dissolve in hydrogen bonded liquids in this way. This is a partially polar, or this is a polar molecule with partial polarity. You mix a fully positive and negative charged molecule in there, and it can break up apart and dissolve. Anything that can participate in this hydrogen bonding, anything that can do this partially negative, partially positive bonding trick, or partially negative, fully positive, partially positive, fully negative bonding, anything that can participate in this pluses and minuses game, you refer to as being a hydrophilic molecule. Hydro meaning water. This was all discovered first in the context of water, so the word water gets stuck in with it. You can apply this principle to stuff that doesn't involve water, but again, life is all water, so we don't care about that so much here. And philic is loving. If something cannot participate in this hydrogen bonding, if you have a non-polar molecule mixed into here, then it's hydrophobic. Phobic meaning scared. Oh no. It's hydrophobic. Oil, for example, has very large chunks of its molecule that is completely hydrophobic. It has a little philic head, but most of it's phobic. When you put oil into water, they don't mix. Oil does not dissolve in water. Instead, you put a big glob of oil into a bucket of water and it balls up on itself, right? What you think about, how you talk about it, is that the water and the oil repel. That's not really the case. What's really the case is that they just don't have anything in common to mix. Hydrophilic stuff wants to participate in hydrogen bonding with other philic stuff. Charges want to attract charges. If you put something that doesn't have that charge into a chargy type of environment, a polar type of environment like water, they just don't know what to do with each other. Water was looking for polar stuff. The oil's not polar. It's just, okay, fine. And it doesn't let it distribute itself throughout the water. It's not so much that the water is rejecting the oil or the oil is rejecting the water. It's just you put the oil in the water, and since the water it's in can't do anything with it, it just sort of stays there together. A classic example, and something you really need to keep in mind this semester, is that the two strands of your DNA are held together with hydrogen bonds. So if you recall from biology class, Intro to Bio, you have your DNA. When it's untwisted, it looks like two rungs. It looks like a ladder, basically, right? Actually, let's do it the proper way here. You have one strand with its nucleotides and another strand with its nucleotides. I'm not going to do this very neatly, I'm sorry. Other strand with its nucleotides. The nucleotides are bonded to the backbone by covalent bonds. Those are extremely strong. You think of them as basically being unbreakable. But down the middle, these are all attracted to one another by hydrogen bonds, either 2 or 3, depending on what nucleotide we're talking about. Each one of these hydrogen bonds is pretty weak. An enzyme or some other molecule in the cell can pretty easily come in and break one nucleotide apart. But together, the sum of all of these hydrogen bonds down the middle keeps your DNA strand quite nicely attached on both sides. And it's going to require a fairly big, robust set of enzymes to come through and fully unzip your DNA.